Hello class, welcome to our lesson today dealing with section 6.3. This deals with the normal distribution things that we looked at in section 6.2, dealing with our chart that we looked at with the z-score table. And then we're going to apply it to other cases that are not necessarily hovered around 0 for a mean and standard deviation of 1. The main idea for what we're going to look at is we want to transfer everything into a standard normal distribution. So the key things here is we have to know mu and sigma, the mean and standard deviation. If we know those things, then we can convert any normal distribution that's a bell-shaped curved idea to a standard normal curve. And then we're just going to use this formula right here. So we're going to change it to a z-score by taking my data point x minus the mean and then divide by standard deviation, which essentially says how many standard deviations are you away from the mean. If you get a negative, you're below the mean. If you're a positive, then it's above the mean. We're going to round these to 2 decimal places, and that's strictly so that we can use the table that we've talked about already. And it will work well with what's given to us from that situation. These questions will have a lot more words compared to what you've probably seen in the standard normal distribution questions. So for example here, this says the typical sedan car is built for people that are 6 foot 7 inches. First thing that you want to deal with is to change that just into inches because the mean and standard deviation below are in inches, so that's 79 inches. Because men on average are taller than women, typically when you look at these numbers, it's just the men's heights that are looked at to see if changes need to be made. So sorry about that, ladies. It's a matter of on average men are taller, and so they look at that number and see if that dictates anything. If it fits whatever percentage of the men, that's going to fit probably a higher percentage than of the women. And so that's something that you want to look at in this situation. The heights of men have a mean, so here's the mean of 68.5, standard deviation of 2.85. Find the percent of men that would fit in the sedan. So what I'm looking for here is I want the probability that x, my value, is less than 79. I'm going to find the z-score by taking my data point, 79, minus the mean, divided by a standard deviation, rounded to 2 decimal places, which would be 3.68. So instead of finding x is less than 79, I'm going to do z less than 3.68, which now means I can use my table. So I go to 3.68 on the positive side. That should be the 3.5 and above, and that's 4 nines in a row, which is 0.9999. And that's area to the left because it's a less than. And so over 99% of people will fit into the sedan. Would it be beneficial to make it so it would fit everyone up to 610? Not really, because it already fits a huge amount of the population anyway. And if you're that tall, you're probably not looking for a smaller vehicle at that point anyway. And so then you'll be looking at a different type of vehicle, which explains why companies tend to make different types of cars for different types of reasons. And this could be one of those reasons. This one is about birth weights. So birth weights have a mean for 3,400, standard deviation of 475. We're looking for ones that require special treatment are less than this 2450 or more than 4380. So I just need to find the z-scores for both. And so I take my data point, 2450 minus the mean divided by standard deviation. I get -2. I'm looking for less than -2, which is what my table gives me. So I go to -2 on my z-score, find the 4-digit probability on the inside, and it's just over 2%, this number right here. For the higher end, you got to make sure you do 1 minus because it's a greater than scenario. I take my data point minus the mean divided by standard deviation. I get, notice this is slightly higher, 2.06, which kind of correlates to the idea when a baby's born. If they're underweight, that's probably a larger issue than overweight. Now, it's still an issue if it's extremely higher than normal, but it's less of an issue than the underweight category. Notice here it's a greater than, so z greater than 2.06, which means I have to do 1 minus because the table always does less than or area to the left. I need area to the right, and so that would be 0.0197. And then when I add those together, I get 4.25%. Pay attention to your homework questions. If it says decimal or percentage, you may have to multiply by 100 to make sure it's a percent question as opposed to the decimal. So the 2 questions that we looked at were find the z-score and find the probability, which would use this first formula. If you just do a little bit of algebra, multiply sigma to the other side, add mu to both sides. If you're going backwards, you might have to find a cutoff or a data point. And so you use the second version of the formula. It's the exact same thing, just algebraically moved around. And so you can use that to find answers if you're looking for data points specifically. So here would be one suggestion or question that deals with that. This says that common criteria for design buildings is make sure 95% of the population it fits for. This would be similar to the sedan type of idea. So how tall should the doorways be if 95% of men, which would then correlate to a larger amount of the population, because women on average are shorter. 95% fit through the door. Okay, the heights of men are normally distributed, same mean, same standard deviation as before, 68.5, 2.85. But in this case, I'm working backwards. So I want to make sure I find the z-score that correlates to that. So I'm looking for whatever is less than 95%. Okay, so I'm looking for 0.95 in the table. So I'm looking for the 4-digit number in the table. Now, 95% is one of the strange ones that start and has a line and an arrow. This is one of the few cases where it will go 3 decimal points instead of 2. So you want to make sure you notice that. Look in the table and make sure you know how to find that this is 1.645. Once I have that, I just plug into the formula from this slide. I have the mean, I have z, I have the standard deviation. I plug all of those in, and I get 73.188, which is about 6'1", which probably is not enough. So this is why they go further than 95%, because if it was 6'1", I, for example, couldn't fit through the doorway. Now, things like submarines and smaller areas, they might have smaller doors that you have to duck a little bit. But when you design the building, maybe a common criteria should be a little bit higher if you're looking at that. So that's just something you want to think about. Notice this is working backwards. So I'm giving you the probability. You find z in the on the edge of the table based on the numbers in the middle of the table, and work backwards to find my x term. This next one says we want to separate the lowest 3% and the highest 1%. So lowest 3% would be area to the left is 0.03. I look for 0.03 in the table. I look for the closest one. The closest one should be z equals negative 1.88. Make sure you're able to find that in your table. Then I plug into the formula. I take the mean plus or minus z, the z-score I just found, times the standard deviation, and I get just above 2,500 grams for the low end. And so this would be true at any doctor's visit or office. They have a cutoff that says if you're below or above a certain number, then they talk to you more. Okay, for example, if I have my blood pressure checked and it's above a certain number based upon my age and my weight and my height, then they're going to talk to me more about it. And this would be the same idea here. It's not that the cutoff is the 100% guideline, but it's at least a kind of a red flag and a kind of showing like, oh, hey, we probably should look at this a little bit closer. For the highest 1%, notice highest 1% would be a greater than situation, so that would be 0.01 area to the right. I need area to the left, which is 0.99. I look for 0.99 in my table, find the closest one, and that should be 2.33. Make sure you're able to find that in your table. I'm trusting that you're going to be able to look at that. Remember, we're going to use the table for all questions, so there are other methods and other situations and types of answers that you can get with other solutions and ways of thinking. But we're going to focus just on this table, so you got to make sure you're able to use the table to find it. Then the mean plus or minus, or excuse me, the mean plus the z-score times the standard deviation, and this would be just over 4,500. Make sure you round to whatever it tells you to round to in the homework as well. So that's some applications of going forward and backwards. So you're either going to have to find the z-score and then find the probability, or they'll give you the probability, you work back and find the z-score, and then find the x or the data value that's originally started with that. You're going to want to make sure that you can move through that process fairly quickly. It's not that it's a speed game, but you have to be comfortable with that because we're going to keep using this idea over and over the next couple lessons. So you want to make sure that you're able to find the z-score values and interpret from the graph and the table appropriately. Have a good day, everyone.